In this video, we're going to talk about linear regression with Desmos. Now, we'll begin with an example from MyMathLab. The problem says the table lists the average monthly cost to workers for family health insurance for various years. And you can see a table over here where it lists the years from 2009 up to 2014. So 2009 is considered year 0, 2014 is considered year 5, and the average monthly cost to workers for family health insurance. So in 2009 it was $299 per month, and then in 2014 it had grown to $408 per month. Now we're going to be using Desmos to do this. So the first thing we'll want to do after we pull up Desmos is to click on the plus right here and then click on table. And notice here we have a table with columns x1 and y1. So we're going to enter our values from MyMathLab. Now in the x1 column we're going to put the years. Now remember the first year was 2009, but we considered that year 0. So just type 0, hit enter, and then we'll go 0 through 5. And in the Y1 column, we're going to put the health insurance cost. Now remember year 0, which was the year 2009, the cost was $299 per month. Okay, I've entered all the data now. At this point, we should have some ordered pairs that are graphed on Desmos. For example, the order pair 0, 299 should be graphed and 1, 340. But notice, of course, we can't see these because 0, 299 is way up too high. Now, our problem is not the x values, the domain. Our domain we can see all the way from 0 to 5, but our range is way up here. So we need to be able to include 299 all the way up to 408. So what we're going to do is click on the graph settings and we'll change our y-axis to be, let's let it go from negative 100 up to 500. Okay, and now you can see the data points plotted. And notice that these data points are roughly linear. Now what we would like to do is to find what's called the line of best fit. Okay, a linear regression model that models this data. So how can we do that? Well, remember that a line has the equation y equals mx plus b. Okay, so in Desmos, what we're going to do is type y1 to represent this column y1. And the way you get the subscript 1 is to just type y, then the number 1, and the 1 automatically is a subscript. Then we'll need a tilde. Now this tilde means y1 is modeled by or is predicted by, and we're going to put like an mx plus b, but it'll be mx1 plus b. Now how do you get the tilde? Well, the tilde is should be to the left of the number 1 on your keyboard, and you have to click shift in order to get it. Equals mx1 plus b. Okay, and notice it gives us this line. Okay, this is what's called the line of best fit. Okay, now down here we have some parameters, and notice it gives us the m and the b. So the slope of this line is about 19.8857. Okay, and the b, the y-intercept, is up here at 308.619. Now, what does it mean to say that this is the line of best fit? Well, notice that these data points don't all lie along this line. In fact, maybe none of them lie along this line. But notice they're not too far from the line. In fact, if you look at the vertical distance between the point and the line below it or above it, that number is called the residual at that point. And we're trying to minimize the residuals. Well, technically, you're minimizing the squared residuals. So you take these distances and you square them, and you're trying to minimize that. And so we're not going to go into all the details about how this line is calculated, but this line minimizes those squared residuals. Now you'll notice over here that we have some other numbers. We have this R, for example, is 0.9829. Now R is called the correlation coefficient, and R can range from -1 to 1 depending on what your data is. Now, if the R is close to 1 or close to -1, that means that your data can be modeled well by a line. And notice our data can be modeled very well by a line. It's very close to being linear. These dots are very close to the line. And so an R close to +1 means that we have a positive slope of this line, and it's modeled very well. Now, if the data were really scattered about and you couldn't really model the data well by a line, you'd have an R that's close to 0. Okay, if the R was modeled well, very well by a line that had a negative slope, the R would be very close to -1. So let's look at a website here. This is the QMath website here. I want to give them credit. So notice that this is a perfect positive correlation. All these dots lie along an exact straight line here. So in that case, the R would just be equal to 1. This has a strong positive correlation. So even though we can't find a line that goes exactly through all these points, we can find a line of best fit. And this has a strong positive correlation, so I would expect our R to be 0.9 something, maybe 0.95, something like that. This has a weak positive correlation, so we could find a line of best fit, but it wouldn't fit it really well, so maybe the R would be something like 0.5 or 0.6 or something like that, or 0.4. Now here there's no correlation among the data points, and so we can't really find any line of best fit, so we just say the R is 0. Here we have a weak negative correlation, so this would be an R of like negative 0.5 maybe. Here we'd have a strong negative correlation, so the R would be something like negative 0.9 something. And here, if these data points all lie along an exact straight line, we'd have perfect negative correlation, and the R would be negative 1. Now, I should point out there's also R squared in this table, and we're not going to go into that, but R squared is called the coefficient of determination, and it's basically just this R value if you square it. So if you square 0.9829, you square it, you get this. So let's go back into MyMathLab and answer the questions. So part A says the linear equation of the regression line that best models the data is, well, it should be y equals mx plus b, and it turned out that the m was 19.8857. Now, if I type 19.8857, it's probably going to mark it as wrong because it says round to the nearest hundredth. So this should be 19.89. Okay, and the b, it turned out, was 308.619. But instead of 619, we should put 62. Okay, let's check our answer. And it says good job. Now let's look at part B. It says predict the average monthly cost to workers for family health insurance in the year 2018. Now our data only goes up to the year 2014, but what would we predict based on this model the average cost to be for health insurance in the year 2018? So 2018 would be considered year 9. And so what we're going to do is plug in 9 for x and then figure out what y is. Okay, and I did that. And I came up with the answer $487.63. Now, it's a little questionable here whether you should use these rounded off numbers, 19.89 and 308.62, or you should use the longer decimals. And you will get slightly different answers if you do that. I just use these two numbers, but I think either way, MyMathLab will mark it as correct. So $487.63 you get one way, and you get like $487.59 the other way. And I think it will mark both as correct. But I just used this equation and plugged in 9 there for x. Now it also says compare the value with 460, which is obtained using the points 1, 340 and 4, 385. So notice we have these two data points here, 1, 340 and 4, 385. And if we were to just draw a straight line through those ordered pairs, what would that give us at year 9? Okay, and it turns out it would give you $460. Now notice that's not the same as this. Okay, so we expect this model probably to be better or to have more predictive value than if we just take those two data points here. So notice, what can we say? Compare the above attained value with $460. So $487.63 is greater than, right? It's more than, it's $27.63 more, $27.63 more than 640. Let's check our answer, and it says excellent. Okay, and the correlation coefficient, that would be the R. What is the R? Well, we found the R to be 0.9829. So 0.9829, but it says round to the nearest thousandth. So this should be 0.983. Check our answer. And finally, does the regression line fit the data closely? And it actually does. Notice that those data points all were pretty close to that straight line. And so what we can say is, yes, the line fits the data fairly well as the correlation coefficient is close to 1. Okay, so that's our answer. The correlation coefficient was 0.983. So since it's close to 1, it fits the data well.